Hello, bonjour, Mingalabar, Kemche. Welcome to the 9th tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale supérieure. The Monte Carlo method that we have mastered in the last 2 months and a half in classical and quantum system has far outgrown its origins. In this week's lecture already, we study time-dependent phenomena and faster-than-time algorithms. Today, Monte Carlo methods are literally everywhere in science and engineering. And time has come to present at least one application in a wider context of these methods. The application that we have chosen is concerned with optimization methods. For concreteness, we consider a problem that is familiar to all of you and to all of us. You know what it is? Well, it is the packing problem that builds the logo of our course. What you see here is a red unit sphere and a bunch of blue unit spheres around it. All of the blue ones touch the red one, but none of the blue ones overlap with each other. So the question is, how many of the blue unit spheres we can place around the red unit sphere? So let's find the first solution to this packing problem. What you see here are 6 blue spheres grouped around the central red sphere in its equatorial plane. Now we add 2 more layers, one on the top and one on the bottom. In fact, we put 3 more spheres on the top and 3 more spheres on the bottom. All of these spheres touch each other, touch the red sphere, and we have 3 plus 6 plus 3. That means we have found a packing with 12 spheres. As you already saw in the logo, we can distort this packing a little bit and create space around the blue spheres. Let us find a second solution. Now not with 3 layers, but with 4 layers. We start with 1 sphere at the bottom. We add 5 spheres on the second level, then 5 spheres on the third level, and then a final sphere on top. Now we have 1 plus 5 plus 5 plus 1 sphere. All of them touch the red sphere, but in this icosahedral packing, none of them touches each other. Again, we can make a little space, and the question arises whether we have enough space to add a 13th blue sphere to this ensemble of 12 spheres. This is the famous 13-sphere problem, and it was first discussed by Newton and Gregory in 1694. So clearly, there are different packings possible, and you understand that a sampling problem is just around the corner. So, from a wider perspective, the subject of this tutorial is the relationship between this sampling approach and, for once, not with integration, but with searching and orientation in complicated configuration spaces. Next, in this tutorial, Michael will show us how to formulate the packing problem, not in terms of spheres on the surface of a sphere, but in terms of disks on the surface of a sphere. Then we will go on to discuss strategies, to find solutions that were once so well hidden that before the advent of Monte Carlo methods, it took years and decades to find them.
Let us transform the problem a little bit and search for the maximal radius of 13 blue outer spheres of radius capital R around a central red sphere. If this maximal radius is larger or equal to 1, then there is enough space for Newton's 13th sphere. Otherwise, not. As Werner just explained, we can simplify the problem a bit by considering the projections of the 13 blue outer spheres onto disks inside the red sphere. Let us start by considering the simple case with only 2 blue outer spheres touching each other and the central red sphere as is illustrated here. The centers of the 2 blue disks are a distance of 2 capital R apart, while the centers of the projection disks are a distance of 2 lowercase r apart. You can see that 2 uppercase R relates to 2 lowercase r, like 1 plus capital R relates to 1. You might remember this relation as Thales' theorem. It gives us a simple relation between the radii of disks touching on a sphere and spheres touching on a sphere. It is given by R equals 1 over lowercase r minus 1. Likewise, you can see that the disks have to be at least a distance of 2 lowercase r apart, lest they overlap. So let us now follow our winning strategy of the last 2 months. We randomly sample the 13 positions of the blue disks on the surface of the unit sphere. In a first, naive approach, we uniformly sample these positions and check for overlaps. Of course, we are only interested in legal configurations, that is, configurations of non-overlapping disks, and we reject in case of an overlap. In Python, this direct sampling approach can be implemented as is shown here. Of course, this program works and will eventually give us legal configurations of 13 disks on a sphere. This works very well for small radii lowercase r, but it suffers from a huge rejection rate for larger disks. Already for disks of radius lowercase r equals to 0.32, the program will generate 10,000s of illegal configurations before finding a single legal one. For disks of radius lowercase r equals to 0.34, the program will generate hundreds of thousands of illegal configurations, and for r equals to 0.36, it will generate more than 10 million illegal configurations. This value, lowercase r equals to 0.36, corresponds to a sphere radius capital R equals 0.5625. And you will see in a few minutes that this is still far away from the close packing situation. The problem of finding legal configurations of disks on a sphere is related to the problem of finding legal configurations of hard disks in a box, as we considered in week 2 of this course. You will remember that in tutorial 2 we discussed the program directDisks any.py, which allowed us to first place points in the plane and only then to compute their minimal distance and density. We can adapt this program to our needs by placing the points on a sphere using the Gaussian random numbers we learned about in week 4 of this course, and then computing their minimal distance. This gives the Python program shown here. So, is there a smarter way to generate large radius configurations? Of course there is. Alberto will in a few moments explain a method to use a Markov chain algorithm for this purpose. But before moving on, please take a moment to download, run and modify the programs directSphereDisks.py and its alternative version directSphereDisks any.py that we discussed in this section.
Now, after the direct sampling, let's go ahead with the Markov chain sampling, following our 9-week-old strategy for tackling difficult problems. In Python, this gives Markov sphere disks.py, where here we start from a legal configuration of points on the sphere and propose little moves which are accepted if there is no overlap, so that during our Markov chain simulation the disks never touch. This suggests that we should slightly swell the disks at certain time during the simulation by a percentage gamma of the maximal increase that would keep the configuration legal. In Python, this is done in the function resize disks.py that is shown here, where we can set the percentage gamma of the maximal increase that we wish to use. Alternating long runs of Markov sphere disks.py with the resize disks.py allows to construct a very efficient program, which is actually a very general strategy, optimization strategy. In our example of 13 spheres, we can see that we can reach density that we never dreamt of using direct sampling. The idea of combining long Markov chain with careful resizing is reminiscent of what in metallurgy we call annealing, which means that we cool down from high temperature a metal very slowly in order to drive out the grain boundaries and the other imperfection, and this makes the metal less brittle. On computer, the name Simulated Annealing was coined by Kirkpatrick, Gellert and Vecking more than 30 years ago in a very famous paper. In our problem of 13 disks on a sphere, each time step is composed by a resizing and 10,000 iterations of the Markov chain. After each resizing, the step of the Markov chain, which is set by the standard deviation sigma of the Gaussians, is automatically adjusted in order to keep the acceptance probability in accordance with the 1/2 thumb rule. We see that the packing density eta slowly increases during a run until the disk settles in a jamming configuration and the parameter sigma goes to 0. Naturally, there are many inequivalent jammed configurations, and some of them are non-optimal, but can trap the simulating annealing routine forever, and this is a clear limitation of the method. However, if you run the simulating annealing routine many times with different random numbers and keeping gamma small, you will observe that the solution is, most of the cases, the highest density solution. This means that the optimal packing configuration has a large basin of attraction. On our problem of 13 disks on a unit sphere, the maximal value of capital R that we can obtain, and actually you will obtain in this week's homework, is capital R equal to 0.91, 64, 67, and so on. With our method, we cannot actually exclude the value R equal to 1. In fact, this is excluded by a proof given by the mathematician Schutt and van der Waerden in a famous paper of 1951. Before listening to Vivien, welcome back Vivien, please download, run and modify the program Simulated Annealing.py that we discussed in this section. Please make sure to understand how the Markov chain is implemented and the function resizedisks.py.
Let us now generalize what Alberto has explained to us, and this will allow us to illustrate the successes of the simulated annealing method, but also its limitations. As a first generalization, let us consider the case not of 13 disks on the sphere, but the case of any number n of spheres around the inner spheres. The program simulated annealing.py can be easily modified, and you obtain the following result for the maximal density eta max as a function of n. You observe that eta max grows slowly with n, but it seems that it does not go to the value eta cloth packing equals to pi over 2 square root of 3, which is the maximal density for the cloth packing in 2 dimensions. However, we would expect to reach this asymptotics since a lot of small disks on a sphere would feel like living in a 2-dimensional plane and thus adopt the hexagonal ordering. Yet, in fact, this method will still reach this asymptotics, and it can be proven that the convergence is very slow. The ratio between the maximal density eta max and eta cloth packing behaves as 1 minus a constant divided by n to the power 1/3. Let us now make an analogy. We can image the jammed configuration as local minima in a vast and complex landscape. The optimal configuration will correspond to the global minimum that we can call the ground state. In fact, many physical problems can be recast in this description, and in general, the method of the simulated annealing will work because if one takes an equilibrium system and sends the temperature to 0, it will adopt the ground state. However, this argument is purely formal, because in practice, simulated annealing cannot be done at a very, very small velocity, which we would require for this method to work always. The nice behavior we have discussed is in fact limited to simple cases, disks, spheres. For instance, in the case of polydisperse disks, the method of simulated annealing does not find the optimal configuration, but still finds good configurations. In real life, simulated annealing must be practiced with care, especially in cases where there are imperfections and disorder, because then there are a lot of metastable states, and the system may be stuck in them. If the imperfections are too pronounced, the result of the algorithm is very often a glass rather than a crystalline matter. For the case of the polydisperse disks on a sphere, that is to say, disks with varied radius, this is what happens. The disorder prevents the system from reaching its optimal configuration and leads the system into one of the jammed configurations whose basins of attraction is much larger than in the case of the monodisperse disks. Before continuing, let me grab the object of the week, the flip die, and let's flip it faster than the clock.
Okay, so in conclusion, we have studied in this tutorial 9 one of the many connections between statistical mechanics and the rest of life. You will continue the subject of packings in this week's homework, but don't forget that there is a connection between sampling not only with integration, as we have studied throughout this course, but also with searching and orientation in complicated spaces. So finally, have good luck and a lot of fun with homework session 9, the final homework session of this course. Next week, we will have a lecture on the alpha and the omega of Monte Carlo, and the final tutorial will be devoted to a review and to a big party. And thanks again for your interest and for the very active part that you are taking in our course.